Hello and welcome in. This is going to be a new video series that we're exploring. The format can kind of probably change over the first couple of videos as we go through. Basic idea is to work through math topics slowly for everyone to kind of follow along. If you're a faster learner, you can of course hit the 2x speed button. Today's lesson, we're going to get into Newton's binomial theorem. And some things to keep in mind before we jump in is that there is a set of notes you can download in PDF form and in Notability form, and that might make it a little bit easier to stay actively engaged as we move through the content, and it'll just kind of help you retain everything that we learn. So, content you should probably know before we start this topic, some prior knowledge. It would be helpful to know your arithmetic and geometric sequences and series. Another topic you should be familiar with is combinations and permutations. And it would also be helpful if you were familiar with the regular binomial theorem, which is what we're going to start with actually. So if you're not familiar with any of those three things, you might find that as we move through content, it'll be a little bit harder, but for the most part, we'll try to kind of talk about those things a little bit if you haven't seen them in a while. And as always, make sure you have something to drink, that you stay hydrated as we move through this video, and get up and walk around. Don't sit for too long. So, we're going to start off with hopefully something that looks familiar. So what we have up here on the screen first is an expression, and this expression is what we would call a binomial. Bi meaning two, nomial meaning terms. We have two terms, and that binomial is being raised to a power. And so the very first thing that we might think about is, how do we take a binomial like this and expand it out? If you've been in algebra for some time and you're looking at a video for Newton's binomial theorem, you've probably seen this quite a bit, and this should be pretty easy to do. We're just taking our expression, which is 4x plus 1, and we're multiplying it by itself, like that. And so to do that, we can FOIL out or distribute out, and we get an expression that is 16x squared plus 8x plus 1. And so this is an example of taking a binomial and expanding it, binomial expansion. And we kind of take this process and we go further and further. So one of the things we could also take a look at is, what if this expression was raised to the third power? And so we could repeat the process for this one as well. We could take our binomial once again, and we can multiply it by itself 2 times. And of course, we're pretty lazy. So to do this 2 times means we have to FOIL out twice. And instead of that, we say, well, is there a faster method that we could use to do that? And that kind of brings us to the binomial theorem, or the start of the binomial theorem. Particularly, we think of Pascal's triangle. So this expression right here, we could take the long way, but there's a shorter way, and that shorter way is to take a look at Pascal's triangle. So what we recognize is that if we were to expand this out fully, our full expression would be 1 times 5x raised to the third power times 2 to the 0th power plus 3 5x raised to the second power 2 raised to the first power plus 3, 5x to the first power, and 2 to the 0th power, the second power, and then finally 1 times 5x raised to the 0th power, and 2 raised to the third power, like that. So we kind of skip this step, and what we can say is that we know that this is true, or we get this result, because these terms that we see here, the coefficients at the front, 1, 3, 3, and 1, come from Pascal's triangle. So Pascal's triangle, you might remember or might recall, is this pyramid of numbers. Let's see if we can get an image up of this. That is way too large. Let's see if we can make it a little bit smaller. So Pascal's triangle looks something like this. And let's make that text a little smaller as well. Pascal's triangle looks something like this. And what we notice is that if we're doing a binomial expansion to the third power, so if we take a look and we recognize that here we're doing to the third power, that means we're going to the third row in our triangle. So this is the third row. Our top row is the 0th row. We're into our third row. We're grabbing those coefficients, 1, 3, 3, 1. And then we're taking our first term, our 5x, and we're putting that to the highest power. And then here to the second highest power. And then here to the next highest power after that, all the way down to 0. We take our second term 2, and we do the same thing, starting with the highest power on the right side, moving to here, 1 power lower, and down until we get to 0. And this gives us the binomial expansion for this right here. So this is, again, still the regular old binomial theorem, doing a binomial expansion. And what we might ask next is, well, we've seen it for, the power of 2 to the power of 3. What happens if we have it to a much larger power? Maybe it's to the power of 10. How could we use this Pascal's triangle to do that? So let's grab another expression. This one is going to be raised to the 10th power. So we have 4x plus 1 to the 10th power. What we can probably see right away is that if we take an expression and we raise it to the 10th power, we need to go to the 10th row in Pascal's triangle. And so once again, that's a long, tedious process. And instead of using Pascal's triangle, we instead recognize that Pascal's triangle has this combinatorics representation. So every single number in Pascal's triangle also has a combination representation. For instance, the very 0th row of this triangle can be represented by 0, choose 0. So we can imagine that if we're doing an expansion all the way to the 10th power, what we should do is then go down to the 10th row, and we can imagine that on the 10th row, our very first number is going to be 10, choose 0. And just like with the pattern we saw before, we then take our first term, 4x, we raise it to the highest power 10, and we take our second term, 1, and we raise it to the 0th power. And so just in that way, we can start to build out the expansion for this binomial. Our next one would be 10, choose 1, and 4x to the 9th power, and then 1 raised to the 1 power. And we could do this all the way until we get to our very last term in the expansion, which would be 10, choose 10. Our first term, 4x, raised to the 0th power, and 1 raised to the 10th power. So using these methods, first regular old distribution, and then 2, Pascal's triangle, and then 3, the combinatorics representation of Pascal's triangle, we can expand any binomial up to any power. But one thing you might have noticed as we went through all of these examples is that the powers that we are using, so 2 and 3 and here 10, all of those numbers are positive integers. And so the question that might be kind of at the back of your mind as we're working through those problems is, well, what if those numbers weren't positive integers? What if they were something else? Before we answer that question though, let's go ahead and put the regular old binomial theorem formula up on the screen. Let's see. So here is our regular binomial theorem, just like we talked about, and you can use this to expand any binomial up to any power as long as it's a positive integer. And a positive integer is any number starting with 1 that's a whole number and continues on up to infinity. And this is oftentimes written as the set z, or z plus, for all the integers, all the positive integers. So what we're saying for the regular binomial theorem is that it's kind of limited. It only works for this set of numbers. Newton was investigating calculus and noticed some patterns in some of the formulas he was working through, and he thought maybe somehow that this formula might extend to fractional negative powers and negative fractional powers. And so that kind of brings us to our main question for this video, which is, what if the exponent was not a positive integer? What could that mean, and what could the expansion look like? So we kind of just saw above, for positive integers, it makes sense. We're taking something, we're multiplying it by itself, and so to expand out, it's kind of an obvious result. But to raise something to a negative power or a fractional power, that seems quite counterintuitive. And so what we have to do is kind of go to a place that's a bit unexpected, and that place is to sequences in series. And that's kind of why we mentioned that at the beginning of the video. So to answer this question, well, I guess we should put up some examples, right? So some examples of a binomial raised to a non-positive integer could look something like this. And we don't need that. Oh, we lost something with that. Let's just delete that. We might have some binomials that look like this. Maybe this raised to the 3/4 power, negative 3/4 power, maybe to the 1/2 power, maybe to the negative 1 power. So by the end of this video, we should be able to expand out each of these three cases. Let's just shrink those down and get those out of the way. So to answer this question, like I mentioned, we're going to jump over to a topic we've seen before, and that topic is sequences of numbers. So we're going to put a sequence of numbers up on the screen and see if you can spot what the pattern is for this sequence of numbers. If you answered with it being exponential growth, that would be a correct answer. If you said that this was a geometric sequence, that would also be a correct answer. If you maybe even said there's a common ratio, even better. If you said that as we move from one number to the next, we can see that we're multiplying by 2 each time, and you said our r is equal to 2, that would be the best possible answer. So specifically, we can say what we're looking at here is a geometric sequence where each term is a multiple of 2 of the previous term. And if we multiply by 2 each time, that's called a common ratio. It's common as we move from term to term, and the ratio is 2. What if we took the terms of this sequence and we added them together? So what if we had something like this? What would be the sum of this sequence? You might know that if we take a sequence of numbers and each number is bigger than the last number, that this sum, if we keep adding terms to infinity, just is going to get larger and larger and larger. So what we can say is that this sequence of numbers all added together has a specific name, and we call this a geometric series. And like we mentioned, if the sequence of numbers gets larger and larger, the sum of adding all these numbers together is also going to get larger and larger as well. All right, let's try one more. What if we had a sequence of numbers that looked like this? Can you spot the pattern for this sequence of numbers? If you said that this sequence has a common ratio of 1/2, you would be correct. So instead of doubling, we're taking half. We're going to keep it pretty simple. And we can say here, our r is 1/2. And if we ask the question, what's the sum of all of these numbers? If we were to do a series for this, any guesses what the sum of this sequence of numbers would be as we go towards infinity? If you said that there is a sum, that's pretty amazing. So what we can say is that this one does have a sum, surprisingly enough, and it's something that we kind of learned about back with geometric sequences. And this is called an infinite geometric series, meaning that we're multiplying by 1/2 as we go across, and we're adding all those terms together, and it seems kind of surprising, but if we add an infinite number of terms, it actually gives us a finite sum, which is pretty cool. And so there's this formula, the sum of all the terms, sum to infinity, is equal to the first term divided by 1 minus the common ratio. So for this series, our very first term is 1, and our common ratio is 1/2. And so if we put all that together, we get 1 over 1/2. And so the sum of all of these numbers to infinity is 2. And so trying to keep focus on what we're getting towards, we're trying to find out how do we expand, again, binomials that look like this raised to fractional and negative powers. And so we kind of went off on this tangent about sequences and series, and weirdly enough, this here is actually going to help us answer this question. So one of the things we've kind of seen is that this one had a common ratio of 2, this one had a common ratio of 1/2, but what if we had a sequence of terms where instead of a common ratio, we just replaced it with something general, or we generalized the result? If we did something like that, we could get a series or a sequence that looks like this. So we're saying that we have some terms. The very first term of the sequence is 1. The next term of the sequence is r. So instead of changing it to maybe multiplying by 1/2 or 2, we're going to say just the ratio, whatever we decide to be later. It could be a 5, it could be 6, we can multiply by 3/4, we can multiply by -1. R is going to represent all of those possible cases. The question is, what would the sum of that series be? Well, like we saw before, for this one here, our sum to infinity is going to be, let's do that in black. So our sum to infinity is going to be the first term, 1 over 1 minus r. And in this case, our common ratio is just r. We kept it pretty simple. And so what we're saying here might not look that impressive, but it's actually a really amazing result. We're saying that 1 over 1 minus r is equal to this series right here. 1 plus r squared plus r cubed, and so on. And the reason it's kind of surprising is because it's saying that this expression here is equal to an infinite series. And if we rewrite this just a little bit, we get 1 minus r to the negative 1 power. And hopefully now you see why we spent all this time going it back into sequences and series. We see that that's actually a binomial raised to a negative power. And so this is like the key insight that kind of unlocks everything. It shows us that binomials raised to negative powers, and maybe even fractional powers, have not just a normal expansion like we saw up above when we started this. So back before, we would have, a binomial expansion, there'd be 4 terms. When we raise it to negative and fractional powers, we're actually going to get an infinite expansion. And that's pretty amazing. Now, maybe if you think about something else, for instance, fractions, 1 over 9, that has an infinite decimal representation, so 0.9999999. That's not true. Actually, our decimal representation is 0.11111, and that goes on for forever. So maybe in one way, it's very familiar. We've been kind of seeing infinite representations since maybe elementary school, but this is probably our first time we've seen that an expression or a function, which we'll see in a second, has an infinite polynomial representation. Now there's one other thing we haven't talked about, and that is up here, some of these series with sum to infinity, we'd call this divergent. There's no sum. And then down here, we notice that some sequences have a sum, and we call this convergent. And it does have a sum. We can say the sum is 2. And so the question that we might ask is, well, how do we know if it's going to converge or diverge? The obvious kind of answer is that, well, if the numbers are getting bigger, it's definitely not going to converge. It's going to diverge. It'll get bigger and bigger and bigger. If the numbers get smaller, then it will converge. And so one way that we can show that that's true is to say, well, our r has to then be a value that's a fraction. So each time we multiply from one term to the next, to ensure that the next term is smaller, we have to be multiplying by a number that's less than 1. That's kind of what we're thinking. And so if you remember from geometric sequences and series, there's this condition that this formula, the sum to infinity, it only works if r is less than 1. And more specifically, we're saying that r has to be less than 1 and greater than negative 1. So any fractions that you can think of, negative 1/2, negative 3/4, positive 1/2, if you're not sure about that result, you can try a couple of geometric sequences, create your own, with fractions that are in that range, and you'll notice that all of them do converge, and they do have a sum if this condition is met. So that's a really important condition. And that condition holds down here as well. So we generalized it and we said for any r we can think of, this is going to be true, but r still has to meet that condition of being between negative 1 and positive 1. And so if we take all of that and put it together, we get this result. Maybe we change our r to an x. We can say that 1 minus x to the negative 1 power has this infinite representation of 1 plus x squared plus x cubed, and so on. Like that. And so we've kind of solved our very first binomial raised to a negative power. Now, what if we wanted to do something else? Like, what if we wanted to do 1 minus x to the negative 2 power? How could we do that? Well, we could say that this right here is really just 1 minus x to the negative 1 and 1 minus x to the negative 1. And so we could just take this representation here and multiply it by itself, and that would give us 1 minus x to the negative 2 power. And so in that way, we could do an expansion for any negative integer based on this result that we just found. So for instance, we could take that and put it in there. And multiply that by itself. We should have copied and pasted that other one we already had, but we could put that there like that. And that would give us a result. It would be an infinite number of terms here and an infinite number of terms here, which would be a lot of work to multiply out. So in this way, we wouldn't want to do the entire expansion, but if we had some extra time, what we could do, we could take some time to do, is we could FOIL out very slowly. We'd start with our first term, 1, we multiply by the 1. Take our 1, multiply by the x. 1, multiply by the x squared. And maybe we could go up to the fourth term. And so we get all of our terms. And maybe let's just write a couple out real quick. So, for instance, 1 times 1 would just be 1 plus, let's do that in black, 1 plus x squared plus x cubed. So that would be the first set of terms we'd get. And then we'd add that to the next set of terms. We take x and multiply them by everything. So we get x plus x squared plus x cubed plus x to the fourth. And that would go on for forever. And then we could do the third term. So x squared times everything. So we get x squared plus x cubed plus x to the fourth plus, x to the fifth. And that would go on forever. And what we notice is that the beginning terms, like for instance this 1, that tells us that the first term of our infinite expansion would be 1. And then we have to go into here and gather all the x terms. Well, only the first two have an x. So we could say, oh, it would be 2x, like that. And then we look for all the x squared terms. We say, oh, there's 1 here, and 1 here, and 1 here. So that would be 3x squared. And so by working that out, we could slowly start to build a pattern for 1 minus x to the negative 2 power, and it could help us get a little closer to a generalized formula for binomials raised to negative powers. And then you might be asking, well, what about fractional powers? What would that mean? That one's pretty difficult. So if we're thinking about 1 minus x to the 1/2 power, we know that that is going to be 1 minus x to the 1/2 and 1 minus x to the 1/2, and that's equal to 1 minus x to the 1 power. And that, well, maybe that's not a good example, but this is just some on the fly kind of brainstorming how we might be able to think of a way to do this. We'll leave this to maybe someone else to solve, but if we had this and we had that, this is like right here on this side, this is 1 minus x to the negative 1. And then over here, we kind of see 1 minus x to the 1/2. So maybe with some algebra, instead of rearranging, we could somehow solve this for 1 minus x to the 1/2 and see what the binomial expansion would be for that. We'd expect it to probably be infinite as well. Now, this is just kind of intuition. We're building our intuition. We're answering the question, what does it even mean, again, to have a binomial raised to a negative power or a fractional power? And we went through this whole kind of process of thinking, showing that, well, if we raise something to a negative power, it leads to an infinite expansion. And if we raise it to Other negative powers, like -2, those are also infinite expansions. And maybe with a bit of work, we could even take this and somehow find a representation for fractional powers as well. But we'll leave that up to anyone who wants to give that a try. It could be really easy, it could be really difficult. If you find a way, using kind of this method that we used up here, to find a representation for a binomial race or fractional power using just algebra, high school, college level math, I would love to see it. I think, though, it would take higher level math, probably, what's it called, real analysis, or maybe some calculus with Taylor polynomials. So what we're going to say is we've kind of developed our intuition. This is not a complete proof, right? We've just showed it for raised to -1 and the -2 power. We have not proven it for fractional powers, but we have a guess that it could somehow work. And that's actually enough for us. And Newton was kind of in the same place. Newton did not have a complete proof for this. He had an intuition. Again, he was working through some other math and saw this pattern and thought, wow, maybe the binomial theorem could extend to work for fractional and negative powers and negative fractional powers. So what we could say here at this point is we have the intuition of why this might work, and now we're just going to present the formula. So maybe we're taking a bit of hand waving here, saying that we think it could work, someone else has done the math for us, and we're going to take that result and run with it. So kind of a bit of hand waving, and we're jumping straight from this small intuition into the final formula. So our final formula looks something like this. And let's erase that stuff, we don't need that. This formula is very concise, and it's really beautiful to look at because it takes a really impressive result, all of this math that we just talked about, and it summarizes it all in one nice succinct formula. The downside is that this formula is not very human-friendly. And so if we look at it, especially after a long time of not doing this type of content, it can kind of look like a foreign language. So our very first step, the very first thing we want to do is take this formula and start to break it down piece by piece. So one thing you'll notice is that all the examples we did as we were trying to build our intuition were pretty simple. We noticed here that we just had a 1 and a 1x. And you're probably asking the question, well, what happens if we have other numbers there? What if it's 4 minus 5x raised to the 7th power? How do we handle numbers like that? So we can see here this has been generalized to work with any number as our first term and any number as our second term. And you'll notice as well that there's going to be a constant here, and then this is going to be our x term. So this formula will work as long as you get your binomial into this standard form, like that. So a, some constant, plus b, some constant, times x, raised to some power, where now we can say that n is part of the q, the set q. So that's all numbers, positive and negative. It includes our rational numbers and irrational numbers. Is that true? No. Q is rational numbers only. So that's going to be integers and fractions that we're going to be able to plug in for n. And this will work for all of them. Okay, so this is Newton's binomial theorem. Let's go ahead and break it down. Right up at the front, we have our a, so that's our first term here, a constant raised to the nth power, which is given. And then we have this sigma notation. Sigma notation is great for making concise formulas, but it can be kind of hard to see what it's saying. So let's take this sigma and start to expand it out. So we'll start with our a to the n first, and then we're going to take this expression here and put that in brackets as we expand it. Hopefully you've seen sigma notation. Our bottom number, r equals 0, that's the number we plug in first. So we're going to take 0, and we're going to plug it into here and here, this whole expression. So we're going to get n, choose 0, like that. And then we're going to get bx over a, all raised to the r power, where r is 0, like that. And this is the very first term of our summation notation, if we put it in expanded form. And then we repeat this process. So we take r is equal to 1, we get n, choose 1, and our expression here is bx over a raised now to r is equal to 1, and so we get 1. And maybe we can put up here, r equals 0, r equals 1, r equals 2. We'll just do the first, maybe 3, we'll do the first 3. So r is equal to 3. And so our next one, just like before, n choose 2 now, bx over a, oops, that should be over a, all raised to the second power, and then n choose 3, bx over a again, all to the third power, and then again, keep in mind, this summation goes up to infinity, so this is an infinite series of terms. Our next question is, well, what does it mean to have n choose 0? So down below here, we're going to try to break that down a little bit. Let's give ourselves a little space. And we'll kind of take a look at what it means to do n choose 0. That's getting into factorial. Oops, let's move that there. That's getting into factorial notation a little bit. So if we have n choose 0, another way to write that is n choose 0. We're using our n choose r formula. So n choose r has the formula n factorial over r factorial n minus r factorial, like that. And so here, this is going to be equal to n factorial, n is n, and our r is 0. So we're going to get 0 factorial, and then n minus 0 factorial, like that. And that simplifies to n factorial over 0 factorial is 1, n minus 0 is n factorial. We have n factorial on the top and bottom, which cancel, and that gives us just 1. And this term here is raised to the 0th power, so we can imagine that this whole first term is just going to be 1. We'll simplify down below. All right, let's try one more of these, maybe 2 more of these. What about n choose 1? What do we think n choose 1 would be equal to? Yeah, we're going to follow that same process. So here we do n choose 1. We're going to get n factorial over, again, our r is now 1, so 1 factorial, then n minus 1 factorial. And in our next step, we have to do a little bit more simplification here. We keep in mind that n factorial is n times the number that's 1 less than it. So if you have 7 factorial, that's going to be equal to 7 times 6 times 5 times 4 times 3 times 2 times 1. So what's a number that's 1 smaller than n? N minus 1. And then we get n minus 2. And this is going to continue until it gets down to 1. On our bottom, we have 1 factorial, which is just 1. And then we have n minus 1 factorial, so that's n minus 1. And then a number that's 1 smaller than that is going to be n minus 2. And then again, 1 smaller than that. And that continues again, all the way down to 1. And so we can simplify this whole expression by canceling all of the like terms. So our n minus 1 minus 2 will cancel all the way down to 1 for those two. And that leaves us with a really simple result. This is just n. And then we can repeat this for n choose 2. This will be the last one we do. And we should be able to spot the pattern by now. So this one, again, we get n factorial. In our bottom, we get 2 factorial, and then we get n minus 2 factorial. We simplify that. Again, top is going to be n times n minus 1 times n minus 2, going all the way down. This is going to be 2 factorial. We'll just leave that as that. And then here, we're going to get n minus 2, n minus 1, and n, and that goes on. Oops, that's not true. We're going in the wrong direction. That should be n minus 2, n minus 3, n minus 4. And that goes on down. And once again, if we simplify all that out, we cancel all the factors. All of those will cancel, and we get, nope, make another mistake there. N minus 1 does not cancel. So we're going to get n minus 2 cancel, that cancels, that cancels. And that leaves us with n over 2 factorial, not a question mark. Let's try that again. 2 factorial. And then in the top we have n minus 1. And so you might notice a pattern starting to emerge. And the pattern, if we kind of highlight here, we get 1, and then n times n minus 1 over 2 factorial. And we can probably guess from this pattern what our n choose 3 will be. If you can't guess, you might have just an intuition that we're going to get one more term on top, and then down the bottom we're going to have 3 factorial. So this is kind of what our expansion is going to look like. So if we take all of that and we put it all together, we're going to get an expanded form of this formula. We get a plus b to the n power. Up here we have a to the n out front. And then inside the brackets, let's use brackets, keep it consistent. We're going to have our very first term, which is n choose 0. N choose 0 is 1. And this term, anything raised to the 0th power, is 1. So we get 1 as the first term. Our second term is here, n1. And we know that n choose 1 is going to be n. So we're going to get n here. And if we want, we can even put a 1 factorial down there. We kind of left it out from this step, but it's there. And that will make it seem a little bit easier, the pattern that we're going to see emerge. So we'll have n over 1 factorial, and then we're going to have bx over a, all raised to the 1 power. Maybe we can zoom out a little bit here so we can see everything together. Our next term is going to be our third term. So we have n choose 2. N choose 2 is this right here. So n times n minus 1 all over 2 factorial. And then again we have bx over a to the 2nd power. And we're starting to run out of space, so let's maybe shrink this down a little bit. Maybe put it on 2 lines. So we're saying a plus bn is equal to this. And we can say that our third term, which is this one here, actually that's our 4th term. Did we miss one? Let's see. So we have 1, that's 1. N choose 1 is this one here. That's correct. And then our square is that one. 1, 2, 3. Oh, I can't count. Okay, this is our 4th term. So our last and 4th term is going to be n times n minus 1. Let's zoom back in a little bit. And so we get n minus 1, n minus 2, all over 3 factorial. And then again, we have bx over a to the 3rd power. And so that's the first 4 terms of the expansion. If we needed more terms than that, you can see this pattern. So we notice that, again, for our denominators, we have 1 factorial and 2 factorial, and then 3 factorial. So the next term would be 4 factorial. If we want to look really closely, this one here technically is 0 factorial. 0 factorial is 1, so 1 divided by 1 is 1, and we're not including it. And so this is the expanded version of Newton's binomial theorem. So this is Newton's binomial theorem here. Let's go ahead and, well, we'll leave the brackets there. Let's just copy that down. So this is the expanded version of this formula right here. Let's erase that and erase that as well. Now this expanded version is much more human-friendly. We can make sense of what's happening here, whereas this one, it takes a bit of interpretation. So we kind of have to take it from the really concise format and remember what the math means to get to here. The good news is that in IB Math, this expanded formula is available on the formula sheet, and that's the one that you'll be referring to as you work through questions and problems. And so the expanded version of that, we can go ahead and put in as well in the TAC format, and it looks like that. So here's our concise version, and this one is our expanded. All right, so that is Newton's binomial theorem in concise form, and now in expanded form. There's one last question we have to answer, and that question is something you might have been thinking about for the last couple of minutes, and that is, well, what is the values of x that allow this to work? So in this one here, they've left off their x like that. This is just an alternate way to write the formula. If you have an expression like 1 plus 3x, for instance, what they're saying with this formula is that b is 3x. So that's just something to keep in mind when you're looking at the formula from that formula sheet specifically. But the question we might be asking is, we saw this expression before. There was this function 1 over 1 minus x, and this had an infinite representation, and that representation was 1 plus x squared plus x cubed, going off to infinity once again. And we specifically said that this only works if x is less than 1, or specifically x is greater than -1 and less than 1. So now that we've introduced all of this new content, we have a and b now, how does that change the values of x for which this series representation is valid? Well, this is called the interval of convergence. It tells us the interval, let's not do that. It tells us the interval in which, again, this infinite series is valid. So we call this the interval of convergence. And the interval of convergence is just a fancy name for what we've seen before. Again, this is an example of the interval of convergence. It works on this interval from -1 to +1. And it doesn't include those endpoints. What if we had an expression and it was something like this, 4 plus 3x raised to the -2 power? What would our interval of convergence be for something like that? Well, to answer that question, we can go back again to something that we're familiar with, this right here. And we could say, well, what would happen if we took this expression here and instead of multiplying by x each time, what if we multiplied by 6x each time? So we go from 1 to 6x to 36x squared, and then I think that's 218, and that would be x cubed. So 6 cubed. What would be the common ratio for that series? 216. Okay, close enough. So all we have to do is take our result and plug it back into our formula. So we can say, well, this is a geometric series. It's an infinite geometric series. The common ratio as we move from one term to the next is now 6x. And so our sum of an infinite geometric series is the first term 1 over 1 minus the common ratio, which is 6x, like that. And then we say the common ratio, whatever it is, it has to be less than 1 in order for this series to actually converge to something, for it to be valid. And so if we kind of solve this out real quick, what we see is that x has to be less than 1/6 and greater than negative 1/6. And that kind of gives us an idea of how our interval of convergence will change if we have something like this. What we can say is that this expression here, as long as we can get it into a form that looks like this, it'll kind of show us what our interval of convergence will be. So what we do is we factor out a 4 from both of these terms. And let's get this out of the way. This little example. Let's move it down to the right. And maybe let's box it in as well. We need to make it a little bit bigger. And let's also label that real quick. So this is kind of some intuition that might help us, again, do something more complicated like this. With a little bit of algebra, we can take this expression and we can change it into something that looks more familiar. If we factor 4 out of both of these terms, we get 1 plus 3 over 4x, like that. And then all of this is still raised to the negative 2 power. And if you're uncertain if that's true, try multiplying your 4 into both terms, and you'll see that it does turn back into that expression. So these two are equivalent. And then that 4, now that it's multiplied out front, we can take it one step further, and we can move our 4 outside of the whole expression. So you can say 4 to the negative 2 using our exponent properties. And inside, we have 1 plus 3 over 4 x to the negative 2. And so we can see here that this is going to help us determine our interval of convergence. Just like with our small example down here, where the 6x, that was our common ratio, this right here, that's going to determine our common ratio and what our interval of convergence will be. And so we could do this for another number. We could say, what if it's 5 minus 7x to the negative 4th power? We could again rewrite that, and we'd factor out a 5. We get 5 to the negative 4, and then inside we'd have 1 minus 7 over 5x to the negative 4th. And that number right there is going to tell us what our interval of convergence is. So to do this generally, we say, what if we have a binomial with a number there and a number, a coefficient here in front of the x, and it's raised to the n power? Through factoring, just like we saw above, we can take an a out of both terms. So we get a, 1 plus b over a, x, all raised to the n power. And then we can pull that a out front, so a to the n, and then we have 1 plus b over a, all to the n power. And I left off my x, let's put that in there as well. Let's give ourselves a little more space. So 1 over b x, all raised to the n power. And this b over a, that's going to tell us our interval of convergence. So we say b over a x, like that, has to be less than 1, because this, again, is our common ratio if we were to write out an expansion, and that has to be less than 1 for the infinite sum to be valid. This right here, we can then simplify. We can say x here is going to be less than the absolute value of b over a, and greater than negative absolute value b over a. So if you're ever looking for the interval of convergence for a binomial that looks like this, the interval of convergence will be given by this form, or you can write it in this form, and that would be your final result. So that's Newton's binomial theorem. That's how you find the interval of convergence when the infinite series is actually valid or not. And that's everything you need to know for binomial expansions in the set Q. So that's kind of the whole set of notes. And what we can do now is then try some practice problems and bring all of this together. So let's go down to a new page and we'll take a look at our very first practice problem. So we'll call this practice problem number 1. And for our very first practice problem, we'll keep it pretty simple. We're going to find a binomial expansion for something that we talked about up above. And that is a binomial raised to a fractional power. So the very first thing that we want to do here is we want to recognize that this is a binomial. It's raised to, again, a fractional power, not a positive integer, which means that to expand it, we have to use our new theorem, Newton's binomial theorem, and we're going to grab our extended formula because that one is a little bit easier to work with. First thing to notice is that our expression here is not in standard form. So the very first thing we have to do is take this and rewrite it so that it's in the form given by the formula. In this formula here, we see our value of a. So a is given as -2. B is going to be our second term. It's going to be 5x. And n is going to be equal to 1/2. And so solving this out is just a matter of plugging those values into the formula. So it's really straightforward. So we start with our left-hand side. We say that -2 plus 5x to the 1/2 power is equal to a to the n, where a is -2, all raised to the n power, which is 1/2. And then we open up our parentheses. Let's give ourselves a little bit of space. Move this down. And we say inside our parentheses, our very first term is always 1. Our next term is n, which is 1/2. And then we have b over a, so 5x over -2. Our next term is n, again 1/2. 1/2 minus 1 is -1/2. And all of that is over 2 factorial. And that's multiplied by 5x over -2. And that's all squared. And so this is the first 3 terms of our expansion. If we wanted to, we could take this further. And for now, we'll just put ellipses there. That is our binomial expansion of this expression here. We can take it a little bit further. And our very first term here is going to be the square root of -2. We get 1 plus 1/2 times that is 5x over 4, and that's going to be negative, so that second term is going to be negative. And then we have 1/2 times -1/2 is -1/4, over 2 factorial is 2 times 1. That's going to give us 2. And then we have 25x squared over 4. And taking that one more step down, we have negative 2, square root of negative 2, 1 minus 5x over 4. This is going to be negative 1 over 8. And then we have that times 4, so that's negative 1 over 32. And then in the top, we have 25x squared. And then our next term after that is going to be positive, and that expansion will continue again out to infinity. And let's just bring that in a little bit. So here we have a negative term as well. All right, so what we see here is the very first expansion that we've done. We're taking, again, a binomial raised to a fractional power, and we get our final answer down here. That square root of negative 2 out front does look kind of suspicious, so I want to take a quick look at this and make sure that our expansion is correct. Okay, so what we see here is a pretty interesting result. If we take this binomial and we expand it out, it actually gives us an expansion with a imaginary result. So we're getting rad 2i, and then that's multiplied by all of these terms. And we can multiply the rad 2i into each of those terms, but I think it looks a little bit nicer having it out front. And so that would be our final result. All right, moving down to our second practice problem. I'm going to try one advanced question to see what that could look like. We might not work it all the way through. We might just want to look at the approach for it. So this is practice problem number 2. And we're going to go back and take a look at the interval convergence for both of these. So don't worry, we're getting there. All right, so practice problem number 2. Ooh, I think we lost our text on that. Let's go back. Well, we can cut that as well. Okay, so practice problem number 2. We're again finding the binomial expansion for this expression and the interval of convergence. So I'm going to start off and say, well, this looks pretty unfamiliar, but in some ways it also kind of looks familiar. And just like with that first question, the very first thing we need to do is take this and convert it into our standard form. So maybe at first glance, it looks kind of challenging, but if you see a few of these, they start to get easier. And what we can say is that this is 1 plus x over 1 minus x, all raised to the 4/3 power, like that. And if you remember from our exponent properties, that means that we can take our top expression and write it as 4/3. And our bottom expression is also raised to the 4/3. And then we can take it one step further and we can say that we have 1 plus x to the 4/3. And then we have a second expression, 1 minus x, and that's raised to the negative 4/3. And so we now have them in standard form. And this is not going to be a very quick process. So we have to take 1 plus x to the 4/3, and we have to expand that first. And then we're going to take our second expression, 1 minus x, and we're going to raise that to the negative 4/3, and we have to find an expansion for that as well. And then once we have those two results, we recognize that they're multiplied together. So we're going to have to multiply two infinite representations in order to get our final result. So to save on time and not do that process, we're going to just go ahead and put in the representation here and here. If you're doing this on your own, I do encourage you to take the time to expand out both of those and get your result. For our very first one, we have 1 plus x, and we're just doing this through Wolfram Alpha. 1 plus x raised to the 4/3 power. And it turns out that that can be represented by a small mistake. One plus x to the 4/3 power. Let's see if they can help us do that. Oh, here we go. So this has a representation that is 1 plus 4x over 3 plus 2x squared over 9 and 4x cubed over 81. And maybe we'll do one more term, 5x to the 4th over 243. And that continues on again. It's an infinite series. Our second term is 1 minus x. And that's being raised to the negative 4/3 power. And the expansion for that is 1 plus 4x over 3 plus 14x squared over 9 plus 140x over 81. And we'll do one more. We'll do 455x to the 4th all over 243. And so like we were saying, we need to take both of those expansions and multiply them by each other to get our final result. So we'll start over here on the left-hand side, and let's grab that first expansion. And on our right-hand side, we'll grab our second expansion. And now we're going to get into the process of multiplying out. This part is also pretty tedious, but we can again talk about the approach. We're going to take our first term and multiply it by our first term by the second term. And typically for questions like these, we're again not going to do the entire expansion. That's impossible. We're not even going to do maybe even 10 terms. We're just going to keep it pretty short, maybe to the first 3 terms. So a lot of questions, when you see them in IB, they will specify only expand to the first 3 terms. So if we start to do that, we get a 1 times a 1 here, we get 1. 1 times our second term is going to be 4x over 3, and then 14x squared over 9. And we don't have to go any higher than that. Oh, we're missing a cube here and there. Then we take our second set of terms, so we'll kind of put ellipses here to represent that there's more terms to expand out. So plus, taking our second term now and multiplying to that one, we get 4x over 3. 4x over 3 times 4x over 3 is 16x squared over 9. And then we'll do one more, 4x times that. We're going to get 4 times 14. Let's do this on the calculator, make sure we're not making small math errors. 4 times 14 is 56. So we're going to get 56 x cubed over 3 times 9 is 27. And again, we're not going to do any more terms beyond the x to the third term. And I guess we're doing the first three terms. Actually, we're not going to be including the cube because we have 1, 2, 3. All right, let's remove that last result. That'll make this a little bit faster of a process. So we just have two terms from the next one. Then we take our third term, which is 2x squared over 9, and we multiply that by our first term. So we get 2x squared over 9, and then 2x squared times this first term is going to give us a cubic, and so we don't even have to consider that one as well. So these are the only terms we're considering. We add them all together, and we say that our result is 1 plus 4x over 3 plus 4x over 3 is going to be 8x over 3. And then for our square terms, we have 14x squared, 16x, and 2. So that's 16 plus 16 is 32. So we get 32x squared all over 9. And that's the first three terms of our expansion for 1 plus x over 1 minus x raised to the fourth power, like that. Maybe we should put a little parentheses in there. All right, let's double check that through Wolfram Alpha, make sure we didn't miss anything. So, let's see. 1 plus x, 1 plus x to the fourth power. Oh, we'll do that instead. 1 minus x. And then all of that is going to be raised to the 4 over 3 power. And let's hit that and see what we get out. Hopefully they're going to give us they do. Awesome. All right, so according to Wolfram Alpha, our expansion for the first three terms is correct, and it looks like that. All right, so this is the expansion part of both of our practice problems, and now we want to ask the question, what about our interval of convergence? So we saw above that to find our interval of convergence, where we have an expression a plus bx to the n power, our interval of convergence is going to be given by x is less than the absolute value of b over a and greater than the negative absolute value of b over a. For our expression here, as we saw before, our a is -2 and our b is 5. So a is 2, b is -5. Did we see that correctly? Nope. Our a is -2 and our b is 5. And so it's just a matter of plugging those values in. We get negative the absolute value of b over a, so 5 over -2. Absolute value is going to make that positive. 5 over 2. We simplify down and we say x has to be greater than 5 halves and less than 5 halves. Oops, that should be negative. So that's our interval of convergence. What does that mean? Well, for this representation that we found here, it's only valid if x, again, is between those values there. Otherwise, that series, that infinite representation does not make any sense. Let's apply that down here as well. We have two to check for. Our first one is 1 plus x, where a is 1 and b is 1. And over here we have 1 minus x, where a is 1 and b is -1. We plug those into the formula again, so x has to be greater than absolute value of b over a and less than absolute value of b over a, where this one's negative. We get 1 over 1, so we get -1. And for here, we get 1 over 1 again, so our interval of convergence is the standard one. It's just between -1 and 1. For this case over here, we have a -1, but you can kind of see that it's not going to change anything because of those absolute values. So we're going to get -1 over 1 is less than x, which is less than absolute value of -1 over 1. Those absolute values give us -1 here, and x, and +1. So we can see the interval of convergence for both is this. If there was a case where one of the interval of convergences was smaller, the smaller interval of convergence would dictate what the interval of convergence is for the entire expression. And so with that, we have our IOC, and we're finished. All right, so that is a lot to go through. We started with something really simple at the very beginning. We're just talking about our simple binomial theorem for positive integers. We did a quick recap of Pascal's triangle. And let's see if this will work. Let's zoom out a little bit. There we go. We did a quick review of Pascal's triangle and the combinatorics representation of Pascal's triangle. And we saw that this binomial theorem works for positive integers. And then we asked the question, well, what about if we're raising this to negative powers, fractional powers, or negative fractional powers? And so we didn't really have any idea of what that could mean until we jumped into geometric sequences and series. And we stumbled upon this really interesting result that binomials raised to negative powers have an infinite representation. And that kind of cracked it wide open. From there, we said we could find other ones like to the -2, but to prove it for fractional powers is actually pretty tough. So we're leaving that up to someone to solve for us and hopefully put in the comments down below. If you figure that out, I'd love to see a proof using algebra maybe, or maybe simple calculus. So put your proof in the comments. And so then we said, oh, here's our formula. We're not going to prove it. Someone has done all the math for us. This works for fractional powers, and it works for negative fractional powers. And in this very concise form, we kind of say it's not very human friendly. We expand it out using factorial and combination, and we get our expanded version, which looks like this. One thing you might have asked when we were going through this process is, well, sure, n choose 0 works here, and n choose 1 works here, but how do we know that this works for fractional numbers? And that requires a proof in and of itself. How do we know that this formula works for fractional numbers? And that proof, I think, might also be a bit above our current math level. But again, if you have a proof for this, I'd love to see it. Put a link to it or put your proof in the comments below. Once we got our expanded version of the formula, this is the one that we're going to be using, and we went ahead and applied it to 2 practice problems. Before we got to our practice problems, we talked about the interval of convergence. What does that mean? Why is our infinite series representation only valid for certain x, or certain common ratios? And so we did a little tangent talking about the intuition behind that, and showed how no matter what numbers we have here and here, we can always find the interval of convergence pretty quickly. And then down below, we jumped into our first expansion, maybe the very first time that we've taken a binomial raised to a fractional power and expanded it successfully. And we said that we're only going to do the first couple of terms, so we only did the 3 to save time, but we always keep in mind that this expansion goes on for forever. And then we found our interval of convergence. And then we took a look at an advanced question where we have something that's a little bit more complicated. We actually have 2 binomials, and so we have to find an expansion for both binomials and then multiply that out to get our final result, which we see here. And then we found our interval of convergence. If there's more than one binomial, we have more than one interval of convergence, and it's the smallest interval of convergence that will dictate the interval convergence for the entire expression. All right, if there were any questions you have, if there's any mistakes in the math, I want to hear about them, put them down in the comments below. And I will see you in the next one. All right, bye.